Okay, so now let's talk about the algebra of limits. There is a couple of simple things that you need to learn about the algebra of limits. And what that is that algebra of limits. So basically in all of these illustrations that we have done so far, we have observed that the limiting process respects addition, subtraction, multiplication, and division. And basically we saw that, for example, we saw that the limit of, for example, x as x tends to a, for example, plus the limit of, for example, x squared as x tends to a was equal to the limit of x plus x squared as x tends to a, for example. We have seen this example, or we saw, for example, some other example related to multiplication. So so what that means is that we can say that the limiting process respects addition, subtraction, and basically multiplication, and division. And of course, as long as the limits and functions under consideration, the limits and functions under consideration are well defined. Now, of course, we need a little bit more information about the limiting process, so that we can understand why the limiting process basically respects addition, subtraction, multiplication, and division. And that sort of information we don't have yet, because there are a couple of loopholes in the limiting process that we don't understand yet. For example, when we say that there was a sentence, for example, while we were learning the limiting process, for example, there was a sentence that said that, for example, as long as, for example, nothing dramatic happens, for example, between basically the two, between the two, for example, let's say that we had some function over here, the limit of f of x as x tends to a, and we wanted to basically find that, and then we created this table over here, and we said that basically let's basically this is x and this is f of x, and let's suppose that, for example, this is a, and basically from the right we got basically closer and closer to a, meaning that that is a plus, for example, alpha, and this is a plus beta, and this is a plus, for example, a plus gamma, and so on and so forth. Over here we said that, for example, this is a minus alpha, this was a minus beta, this was, for example, a minus gamma, and these over here were basically, for example, f of a plus alpha. This was f of, for example, alpha a plus beta, and this was, for example, f of a plus gamma, and so on and so forth. And the same thing over here, f of alpha, a minus beta, and a minus gamma. And we said that basically and this is basically f of, for example, a minus alpha, okay? And we said that the limit of basically the value of the function at x is equal to a, meaning that f of a must be between basically f of a minus alpha and, for example, f of a plus alpha, as long as nothing dramatic happens between these two inputs, a minus alpha and a plus alpha. Now there is a whole lot of basically detail in this sentence, as long as nothing dramatic happens between these two inputs. And so right now we don't know much about this sentence, and again there is a whole lot of details that we have not learned yet about this sentence, so we don't have enough information actually. And so since we don't have that information, we cannot understand why the limiting process respects addition, subtraction, multiplication, and division. But later, hopefully, we will figure the whole thing out once we know about the actual definition of limits. But for now, to just keep things going, we will learn these four parts of this theorem number 1. Call it theorem 1. And this theorem comes without proof. So the theorem is, let f and g be two functions such that both limit of f of x as x tends to a and limit of g of x as x tends to a exist. Okay, then you can say that number one, limit of the sum of the two functions is the sum of the limits of the functions, meaning that you can write the limit of f of x plus g of x as x tends to a is equal to the limit of f of x as x tends to a plus the limit of g of x as x tends to a. Now, number two, you can say that the limit of difference of the two functions is the difference of the limits of the two functions, meaning that the limit of f of x minus g of x as x tends to a is equal to the limit of f of x as x tends to a minus the limit of g of x as x tends to a. Number three, you can say that the limit of the product of the two functions is the product of the limit of the limits of the two functions, meaning that the limit of f of x, times g of x, the limit of f of x times g of x as x tends to a is equal to the limit of f of x as x tends to a times the limit of g of x as x tends to a. Of course, it is absolutely important to understand why this relationship exists between the limit of the sum of the two functions and then the sum of the limits of the two functions, in order to understand how calculus works. But for now, we just need to postpone it to the near future. And then number four, you can say that the limit of the quotient of the two functions, f of x by g of x as x tends to a is the quotient of the limits of the two functions. Is the quotient of the limits of the two functions, meaning limit of f of x as x tends to a over the limit of g of x as x tends to a, as x tends to a whenever the denominator is non-zero. Whenever the denominator is non-zero, meaning that, I suppose over here, g of x has to be not equal to 0, and the limit of g of x as x tends to a has to be not equal to 0. That's basically the algebra of limits. Now, there is a special case for case 3 that we said over here, limit of f of x times g of x is equal to this whole thing. Now, if one of the functions is a constant function, meaning that suppose that in case 3, basically one of the functions, let's say that f of x is equal to some constant like lambda, for example, then this becomes the limit of lambda times g of x as x tends to a is equal to basically lambda times the limit of g of x as x tends to a. So you can think of this as just one function. For example, something like f of x is equal to 3, something like that. So then the value of the function is going to be constant all over the domain of the function, so it would be always 3, so you can take the 3 out and then take the limit of g of x as x tends to a. Now there is one more part over here, which is basically about the limits of polynomials and rational functions. Limits of polynomials and rational functions. Now about that, basically a function f is said to be a polynomial function of degree n. A function f is said to be a polynomial function of degree n of the form basically f of x is equal to a of 0 plus a of 1 times x plus a of 2 times x squared plus a of 3, for example, x cubed, plus all the way up to a of n x raised to the power n. That's basically a polynomial function of degree n. For example, you can write f of x is equal to, for example, 3x cubed plus 2x squared plus 5x plus 6. That is a polynomial function of degree 3, for example. Which is, of course, now I've written it the other way around. You can write it as f of x is equal to 6 plus 5x plus 2x squared plus 3x cubed. So that is a polynomial function of degree 3, basically. Usually it's written this way, not this way, but usually when you write it, basically when you write it in the general form in this notation, you usually write it this way. Basically they are the same thing. Now you can say that this is the form of the polynomial function where a of i's are real numbers such that a of n is not equal to 0. A of n is not equal to 0 for some natural number n. Okay, so now basically our goal is to find the limit of this polynomial function. So the way that we can do it, we know that basically the limit of x, we know that basically the limit of x as x tends to a is equal to is equal to a, and the reason for that is that hopefully you know the reason, but if you don't, you see over here you can think of this. Of course, this is a function over here. This x over here is a function, is a complete function, meaning that you have f of x is equal to x, and f of x is equal to x is, if I take f of x is equal to y, then it is y is equal to x. So y is equal to x is basically a function, this way, meaning that whatever sort of input you have here, the same output you have over here, meaning that if this is, for example, 2, this is going to be 2. If this is, for example, 5, this is going to be 5. If this is, for example, -5, this is going to be -5, and so on and so forth. So these points over here are always meaning that this is -5, -5. This is 2, 2. This is 5, 5, and so on and so forth. Meaning that this function, whatever you give it as the input, you will get the same number as the output. F of x is equal to x is basically this simple straight line with slope 1, meaning your input is going to be your output. So what that means, and we saw that basically we saw that in the case of almost in the case of all of these functions, I would say, when we were taking the limit of these functions, we saw that basically the limit of f of x as x tends to a was almost always, I just saw one example where this was not the case, and that was a function which was basically one of those functions where you have f of x is equal to, for example, this and this and this, a couple of clauses over here for different parts of the domain. For example, x greater than 0, x is equal to 0, x less than 0, and so on and so forth. I don't know what these functions are actually called, but for this kind of function, I suppose we saw that that was not the case, and the limit of the function as x tends to a was not equal to f of a. Otherwise, in all of the other cases, it was just like this, meaning that the limit of f of x as x tends to a was equal to f of a was equal to f of a, meaning the value of the function at that point. And so basically that's basically why we said in the beginning of this section that the limit of f of x as x tends to a is the expected value of the function, is the expected value f of x should assume at x is equal to a. That's basically what we said over there. And so based on that, what that means that the limit of f of x as x tends to a is, you can say that generally it's equal to x is equal to f of a, unless you have one of those functions where there are basically different clauses for the function, which we are not talking about that here in the case of not in the case of these polynomial functions. These are of course not of that type. So then what that means is that then when you say the limit of x as x tends to a, this function basically gives you whatever input you give it, it's going to give you the same output. So that means that this is going to be f of a. This is going to be f of a. And in the case of this function, what happens is that f of a is actually equal to a, because the function is basically something like this. And you see that, for example, if this is a, then f of a, and this is f of a, then f of a is always equal to a, because, for example, you saw that we had, for example, we said that if this point is 2, this point is going to be 2. If this point is, for example, 4, this point is going to be 4. 2 comma 2. For example, 4 comma 4, and so on and so forth. That means that in this particular function, a is equal to f of a. Always. Always. So then I can say that the limit of x as x tends to a is equal to a. Is equal to a. Okay, so that is basically this part. Now based on the algebra of functions, we said that basically if you have the limit of x squared as x tends to a, we could write this as the limit of x times x as x tends to a, which is equal to the limit of x as x tends to a times the limit of x as x tends to a, which is equal to a times a, which is equal to a squared. And so by induction, and so basically by induction, and you know hopefully what I mean by induction. Induction means that, for example, you see over here, for example, you see over here I have, for example, limit of x as x tends to a is equal to a. Limit of x squared as x tends to a is equal to a squared. Now limit of, for example, x cubed as x tends to a is equal to limit of, for example, x times x as x tends to a, which is equal to the limit of x as x tends to a times the limit of x as x tends to a times the limit of x as x tends to a, which is equal to a times a times a, which is equal to a cubed. So then, based on this, as you can see, you can say that by induction, you can say that the limit of x raised to the power n as x tends to a is equal to a raised to the power n. Okay, a raised to the power n. Now, let me move back up here. I don't have space. Okay, so now if f of x, we said that is equal to a of 0 plus a of 1 times x plus a of 2 times x squared plus all the way up to a of n x raised to the power n. Now let this be the polynomial function. The polynomial function. So you can think of each of these terms as a function, meaning that you can write the limit of f of x as x tends to a is equal to the limit of a of 0 plus a of 1 times x plus a of 2 times x squared plus all the way up to a of n x raised to the power n as x tends to a. And then in the algebra of limits we saw that when basically the limit of the sum of the functions was equal to the sum of the limits of the function. So I can write this as the limit of a of 0 as x tends to a plus the limit of, for example, a of 1 times x as x tends to a plus the limit of a of 2 x squared as x tends to a plus all the way up to limit of a of n x raised to the power n as x tends to a. As x tends to a. Now these are basically, we said that these are real numbers, and of course when you take the limit of a number, the limit of a of 0 as x tends to a is that number itself, because you can think of this as a constant function. For example, f of x, for example, is equal to 3. So if you have f of x is equal to 3, you would have this line over here. This is f of x is equal to 3. Now over here you can see that as if I take the limit of f of x as x tends to, for example, 2, it's going to be equal to 3. And if I take the limit of, for example, f of x as x tends to, for example, 5, it's going to be equal to 3. If I take the limit of f of x as x tends to, for example, -5, it's going to be equal to 3, and so on and so forth. That means that I can simply say that the limit of f of x as x tends to a, any a basically, is going to be equal to 3, which is the value of the function, which is basically the value of the function. And so you can say that the limit of, for example, you can say that the limit of, for example, if I call this f of x is equal to lambda, for example, you can say that the limit of f of x, or the limit of, basically, I can say the limit of lambda as x tends to a is going to be equal to lambda, and so therefore I can write basically the limit of a of 0 as x tends to a is equal to a of 0. Is it just a constant number? And so that is that. Now over here I have the limit of a of 1 times x as x tends to a. So I can write this as, basically I can take this out because this is a constant. We saw that basically in the algebra of functions. And so I can write this as a of 1, the limit of x as x tends to a, plus a of 2 times the limit of x squared as x tends to a, plus all the way up to a of n times the limit of x raised to the power n as x tends to a. Now the limit of x as x tends to a, we said that it was equal to a. So a of 0 plus a of 1 times a plus a of 2 times the limit of x squared when x tends to a was equal to a squared, plus all the way up to basically a of n times the limit of x raised to the power n as x tends to a is equal to x raised to the a raised to the power n. So then you can write this as now this thing over here, this expression over here is actually nothing but f of a, is nothing but f of a, because in this polynomial, if you calculate f of a, if f of a would be a of 0 plus a of 1 times a plus a of 2 times a squared, and all the way up to a of n times a raised to the power n. So then you can say that the limit of f of x being this polynomial function as x tends to a, is equal to f of a. Is equal to f of a. That is basically the limit of a. That is actually the limit of a polynomial function. The limit of a polynomial function of degree n. And it's actually the same thing as we have found in the case of even other functions so far. So there is no difference there. For example, in the case of the function, in the case of the function f of x is equal to x, of course this is also a polynomial, so there is really no difference there. So the whole thing basically fits together. That's basically that. Okay, so now about rational functions. About rational functions. About rational functions, basically, the function f is said to be a rational function. So the function f is said to be a rational function if f of x is equal to g of x by h of x, where g of x and h of x are polynomials. Such that h of x is not equal to 0, because you don't want to be dividing by 0. Now the limit of, if f of x is basically a rational function, then you can say that the limit of f of x as x tends to a is equal to the limit of g of x by h of x as x tends to a, which is equal to the limit of g of x as x tends to a over the limit of h of x as x tends to a. And basically over here we showed that if you have a polynomial f of x, the limit of f of x is equal to, when x tends to a, is equal to f of a. So this is equal to g of a over h of a. G of a over h of a. Now there are basically two cases. There are basically two cases that can happen over here, and basically the very main point of these of the whole concept of limits is basically is about rational functions, because you have some polynomial in the numerator, some polynomial in the denominator, and then you divide those two polynomials, and then you will get basically in most cases where the limit is actually useful and beneficial is in those cases where you get 0 divided by 0. The polynomial in the numerator becomes 0, the polynomial in the denominator becomes 0, and then you're dividing 0 by 0. And then basically the art of limit is actually resolving this issue of dividing 0 by 0, which in mathematics for thousands of years mathematicians couldn't find any no solution for that. But then as Newton and Leibniz and all of those people basically individually, of course, worked on the concept of calculus. And of course, back in those days, calculus was a little bit different from what we know today. The definitions were a little bit different. That even the notation was completely different, meaning that if you read the notation of calculus, for example, Newton or those guys basically used 300, 400 years ago, you wouldn't even understand that. It's a funny notation. So even those concepts have evolved a lot throughout these 400 years and now today we have the calculus that we have today. But anyway, for basically this concept of dividing 0 by 0 was this very mysterious concept in mathematics that mathematicians couldn't solve it, and for the first time, well, either I don't really know, there is a whole lot of discussion about this, but either Newton or Leibniz or some other guys basically solved this problem and well, you could say invented calculus basically, and then this problem of dividing 0 by 0 was solved for the first time. So what that means is that basically you could say the main thing that the whole concept of limit does is that it resolves this issue of dividing 0 by 0, which of course ordinarily it's not possible, but somehow limit basically makes it possible. Now what that means is that, so basically we said that the limit of f of x as x tends to a ultimately is equal to g of a by h of a. So now if, of course, sometimes you get basically as the limit of some, for example, rational functions, in many cases, of course, you get some number, for example, like, for example, 3 to 4, 4 to 3, 2/3, or basically 3/2, and so on and so forth. And in those cases, you have basically no problem, and that would be the limit of your rational function. But in some cases, basically your denominator or h of a, so now if in some cases h of a becomes 0, and actually in many cases h of a becomes 0, and then you have, then there are two cases. There are two cases. Number one, when g of a is not equal to 0, when g of a is not equal to 0, meaning that you would get, for example, some number divided by 0. some non-zero number divided by 0, and 2 when g of a is actually also equal to 0, in which case you would get 0 divided by 0. So when g is not equal to 0, so in the former case, in this case, we say that in this case, if g of a is not equal to 0, we say that the limit does not exist. Because you're dividing some non-zero number by some zero number. This is not defined in mathematics. We say that the limit does not exist. Now if g of a is actually equal to 0, then you would be dividing 0 by 0. Now in this case, what you can do in order to resolve that problem, it's basically simple algebra, meaning that you have to rewrite the numerator and denominator in such a way that, for example, those factors that are making the numerator and denominator, you have to basically cancel them out, factor them out and cancel them out, and then as a result of that, then you will get the value, some value other than, of course, 0 divided by 0 as the limit of the function f of x. And basically by notation you can say that by notation we can write, you can basically express it like this, although this might be a little bit confusing until you see the examples. Once you do a couple of exercises or examples related to this, then you will understand this part as well. So we can write g of x is equal to some x minus a raised to the power k times some other polynomial, call it for example g1 of x. So g of x, you can take some factor out. You can take some factor x minus a out, x minus a raised to the power k. You can take this factor out and then write it as, for example, some polynomial of basically of a lesser degree, basically you could say. The product of some polynomial g1 of x of a lesser degree and this factor over here, whatever that might be, that you will see in the case of the examples. Over here you can say basically where k is the maximum of the power of x minus a. We will see what that actually means. This is a little bit not very, I mean, it's not very easy to understand this thing unless you actually use it. X minus a basically in g of x. So where k basically is the maximum of the power of x minus a in g of x. So you have to basically factorize g of x and take this factor x minus a out, and then rewrite your polynomial as some other polynomial times this factor. And then of course you can write h of x, and then similarly you can write h of x. You can write h of x as, for example, x minus a x minus a raised to the power L, for example, times h1 of x, h1 of x, x minus a raised to the power L times h1 of x, as h of x is, as h of a is not equal to 0, as h of a is not equal to 0. Let me write it this way, and we will see what this means. As h of a is not equal to 0, that is also not easy to understand, and there is no way to explain it this way, but we will see what that means in the examples. So basically we rewrote basically the polynomial now becomes, for example, the limit of f of x as x tends to a, as x tends to a is equal to basically g of a, basically you need to write the limit of you can write the limit of basically f of x is g of x by h of x as x tends to a. And then we said that g of x, we could write it as the limit of basically g of x, we can write it as x minus a raised to the power k times g1 of x, for example. And h of x, we can write it as x minus a raised to the power L times h1 of x, as x tends to a. Now what you can do is basically if k is greater than L, then what you will get is basically if k is greater than L, then this part becomes the limit of x tends to a of, now if k is greater than L, then x minus a remains in the denominator. And this becomes x minus a raised to the power k minus L, because k is greater than L, times g1 of x over h1 of x, and so what that means is that then this is equal to basically the limit of x minus a raised to the power k minus L as x tends to a times g1 of x over the limit of basically h1 of x as x tends to a. Now this is basically some this would be, for example, something like suppose that, for example, your polynomial this is something like, for example, I don't know, x minus 2, for example, something like that, raised to the power, for example, raised to the power 3, something like that. So if you have the limit of, for example, this thing times, for example, some polynomial, for example, g1 of x, something like this, as x tends to 2, for example, how would you take the limit of this would be basically this is basically a function, right? So this is actually equal to the limit of This is actually equal to the limit of x minus 2 raised to the power 3 as x raised to 2 times the limit of g1 of x as x tends to 2. Now the limit of g1 of x as x tends to 2, whatever that might be, we're not interested about that. We're not interested in that. But the limit of x minus 2 as x whole raised to the power 3 is basically, you can basically think of that as a function. For example, let's call it, for example, m, or for example, over here we call this f of x. Let's call this f of x is equal to x minus 2 whole raised to the power 3. Now, limit of f of x when x tends to a is equal to f of a. So then the limit of x minus 2 raised to the power 3 as x tends to 2 is equal to basically 2 minus 2 raised to the power 3 is equal to 0. Right? That's equal to 0. So what that means is that this part over here is equal to 0. So this whole numerator becomes 0. So this becomes 0 divided by the limit of h1 of x divided by h1 of x as x tends to a, which is equal to 0. So that means that if k is greater than l, then your limit becomes 0. Now, there is also the case that your k is less than l. If your k is less than l, then this thing over here, this expression over here, becomes the limit of g1 of x over x minus a raised to the power l minus k times h1 of x as x tends to a, which is equal to basically the limit of g1 of x as x tends to a over the limit of x minus a raised to the power l minus k as x tends to a times h1 of x Now, which is basically and this is equal to basically the limit of g1 of x as x tends to a times over the limit of x minus a raised to the power l minus k as x tends to a times the limit of basically h1 of x as x tends to a. Now I suppose this would be, of course we'll see this in the examples, but I suppose then this part would simply be basically 0. So then you would have basically, if this part must be 0, I suppose, so then you would have the limit of g1 of x as x tends to a over 0 times the limit of basically h1 of x as x tends to a, which is equal to the limit of g1 of x as x tends to a over 0. And in this case we say that the limit is not defined. So that's basically the whole story. Now you don't really need to, of course you need to understand this process, but then when you are basically doing the limits of rational functions, you will of course intuitively know what to do. You don't really need to basically really memorize all of these steps over here. Just to understand them is more than enough. Okay, so we have a couple of examples over here, and that's basically about it. So in the next video we will talk about the examples. I'll see you in the next video. Thank you.